course, originally we're not planning on finishing the test at the beginning of this class. So we'll get as far as we can, and then we'll finish that up. Good news is tomorrow's notes we're going to be a little shorter anyway, so we should be able to catch up and stay somewhat on track. So, Unit 2 is going to start into a new section, and it is primarily on logs and exponentials are the main things that we'll be looking at. There's some inverse stuff in there. So logs and exponentials are covered pretty heavily in Math 3. So there should be some things that are pretty familiar. Today, probably not so much, because today is arithmetic and geometric sequences. I think technically they're in Math 1 a little bit, but I know that at least whenever I taught Math 1, I skimped on this pretty bad, did not do a ton with it, and we will go a little further than you would go in Math 1 anyway. So, oh, sorry. I'm forgetting how to use, okay, I gotta hit here. No. Turn on pen, that's what I need. Okay, so a blank is a function from the blank numbers to the blank numbers. So this is a sequence. Is a function from the hold on a second here. That I thought it was integers, but that doesn't make sense. Whole, okay. Oh, I guess it is whole. Integers are negative. Okay, that makes sense now. All right. It can't be negative. Sorry. I have to refresh my memory here. So let's try that again. Let's see. I'll get you a copy of this. Alright, so that should say sequence is a function from the whole numbers to the real numbers. No, oh, I'm still filling in the wrong sequence. We had that there. From the whole numbers to the real numbers. So in a sequence, the numbers that you are putting in are only whole numbers. So there's no 1.5 getting plugged in. It's just 1, 0, 1, 2, 3, 4, 5, and so on for that. I originally was thinking integers, but that would be negatives. You don't use the negatives for these either. So this means that we can only plug in 0, 1, 2, 3, and so on. But we can get any real number as the output. So the answer could be 1.5. The answer could be 2.783. But the inputs are only numbers. Thus, the graph of a sequence will only be points. There will not be lines connecting them.
Can it be negative or no?
You can have negative, like, outputs. Your y coordinates can be negative, but your inputs are always going to be positive for that, or 0. Okay? So, you have been doing sequences since you were small children. For example, here, maybe whenever you were in like 2nd grade, you would not start at -5 or -2. But if you had 1, 4, what's happening each time there? You're adding 3. So what goes next? 7, then 10, and 13. So you've really been doing sequences since you were little, just filling in the pattern for that. So if we look at number 2, okay, what are we doing on that one? Times 2. So the next one would be 24, and then 48, and then 96. For that, just multiplying by 2 each time. Okay, next one's a little tougher. what? Adding 0.65. I believe that looks good. Yep. So if we're adding 0.65, I think I'll grab the calculator for that one just for a little speed here. So if we're adding 0.65, we get 10.2. We get 10.85 and 11.5. Okay, what about the last one? It's times -2. Anytime you see the number switching from positive, negative, positive, negative, positive, negative, you are probably multiplying by a negative number in that case. So if we multiply -8 by -2, we would get positive 16. If we multiplied positive 16 by -2, we would get negative 32. And if we multiplied negative 32 by -2, we would get positive 64. So sequences are just patterns where we are doing something to get the next number, right? What's going to be tricky about these is the notation that we have to use. And the notation kind of throws kids for a loop, but once you understand what the notation means, then that will make the problems much easier to do, because essentially what we're doing is just those patterns that we saw before. So some important notation that you're going to see is you will have a sub 0 is how we read that. It's got a subscript of 0 there. And that's going to be your initial value for the function. That's like 0 is the lowest number we can have because we can't go into the negatives there. So that's going to be sort of like your starting value for your function, or well, for your sequence. N is the whole number that is entered into the sequence. So it can be, the N can be the first number, second number, third number, and so on. It's going to depend on how the sequence is defined, how it gets plugged in. And we'll see that here in a little bit. And then A sub N is the nth term of the sequence. So like over here, A with a 7 behind it would be the 7th term. Or it depends on how it's defined, but like for the 2 examples I have on this page, yes. Okay. If we want A sub 10, that'd be our 10th term for that. Okay, so there are a couple ways that these can be defined here. So whenever we are looking at the problems that we're given here, these are essentially just like functions. The only difference is that we can only plug in the whole number. So you can't have A of 2.7, right? Whereas if I think of this as like f of x equals 3x minus 5, that would be a function, and you could plug any number into it. So you could plug 2.7 into this function, but a sequence you cannot plug a decimal in. It has to be only whole numbers. So when they ask us for A sub 4, and there's an N right here. Yeah. So our A sub N here, if we want A sub 4, we're going to put A sub 4 equals, and that A sub 4 is kind of like saying F of 4. It's just a label. You don't actually work anything out for that. So you've got 3 times 4 minus 5. You just replace your N with the 4. And so you will get 12 minus 5, which is going to be 7.
So you say A sub 4 equals
You could say A sub 4 equals 7. Yeah. Or you can, like I just did a string of equal signs there. That's fine as well. Yeah. Okay. So all you are really doing is plugging the numbers in right there. So if we're asked on the next one to find a sub 2, then we're going to have 2 times 3 squared. And so that, what do I have to do first there? Got to square it first. So I got 2 times 9, which will give me 18 for that. So when your sequence is defined with just an n right there, it is more or less just like a function. It's just different notation that you haven't seen much before. Okay, questions? All right. Okay, now recursive formulas are going to be a little bit different. Okay, recursive formulas are not going to have an n as an explicit variable in the function. Okay, so the difference that we see here in this function is we've got a sub n equals 2a, and then my n over here is in the subscript. Okay, so what's happening here whenever you do this is called a recursive formula. You think of that word recursive, it sounds like recurring. And that is what's happening here. You're doing something over and over and over and over again. If you are given a recursive formula, you are plugging the number in, but you're not going to be able to start with the number that you're looking for. So I want a sub 3. Let me just show you what it looks like if I plug in 3 for my n. So just like with the function, you're plugging in 3 for your n, but you're doing 2, a, and then you'll have 3 minus 1 right here as your subscript, which means that a sub 3 equals 2 times a sub 2. Do we know what a sub 2 is? We do not. So what we have to do is we have to start from the term that we know, and we've got to work our way up to a sub 3 whenever it's defined recursively like this. So they gave us a sub 0 equals 5. So we know a sub 0 equals 5. So let's find a sub 1. Let's find the next term in the sequence. Okay? So I'm going to write this the first time, but you'll see a pattern here where you don't always have to write this. So I've got 2a, and then if I replace that n with a 1, I've got 1 minus 1. And that is going to be 2a sub 0. Right, because 1 minus 1 gives me 0. What is a sub 0? It is 5. So this is 2 times 5. I get 10 for my a sub 1. So we can conclude there a sub 1 equals 10. Now that I found 1, I need to find 2. So I'll do a sub 2. And so that'll be 2 times a sub 2 minus 1. And 2 minus 1 is just 1. So that's 2 times a sub 1, which is what I just found, right? What is a sub 1? It's 10. So it's 2 times 10. And then, which is 20. Then I've got to do a sub 3, which is what I'm actually looking for. So I've got to do 2 times a sub 3 minus 1, which is 2 times a sub 2. What is a sub 2? 20. So 2 times 20 gives me 40. A sub 3 is what I was looking for, so that is my answer for this. Now, you don't necessarily always have to do that much work. Because what was happening here every time, let me see if it'll, I don't think this lets me highlight. Does it let me change colors? Let's see. I want to change colors at least. So if I look at what happened right here, when I plugged in that 1, I got a sub 0. When I plugged in 2, I got a sub 1. When I plugged in 3, I got a sub 2. When I plugged something in for my a sub n minus 1, what did it give me? Not double. Give me the one before it, right? So like when I was plugging in, I was looking for a sub 1, it gave me a sub 0, right? When I was looking for a sub 2, it gave me a sub 1. If I was looking for 3, it gave me a sub 2. So when you see that a sub n minus 1, this is the prior term. Because if we take whatever term we're looking for and we subtract one from it, it's just going to give us the one that was before it, right? So what I could have done here is I can see that this rule is doing 2 times the prior term, right? So for a sub 0, I have 5. 1 is going to be 2 times 5, the one before it. 2 is going to be 2 times 10, the one that came before that. And 3 is going to be 2 times 20, the one that was before that. So you're just multiplying each time. So you can definitely show this work every time, but you don't necessarily have to. So if we look, for example, at number 8, they have us start at a sub 0, and we want to get to a sub 4. Okay, this time my rule is a sub n minus 1, which I can think of as the prior term, minus 4. Right, so if a sub 0 is negative 2, then I'm going to write out the work for this, and then we'll quit using the work. So, like, if I do a sub 1, that's a sub 1 minus 4, which is a sub 0 minus 4, which is going to be, our a sub 0 was negative 2 minus 4, which gives me a negative 6. So notice, all I really had to do right there was take my prior term, which was negative 2, and subtract 4 from it, which gave me a negative 6. So if I wanted to do this a little more quickly, for the next term, for a sub 2, I could take the prior term, which was negative 6, and I would subtract 4, which will give me negative 10. And then if I want a sub 3, I take the prior term, which would be negative 10, and subtract 4, and that'll give me negative 14. And a sub 4 is what they're asking me for. So I take the prior term, which was negative 14, and subtract 4, and I will get negative 18 as my answer. Okay, questions? All right, moving on. All right, so there are 2 specific type of sequences that we need to look at for this class. You can have different sequences, ones that don't fit either one of these, but these 2 are very important mathematically and relate to a lot of different things that we see. An arithmetic sequence, that word is spelled the same as arithmetic, but I believe whenever you use it like an adjective here that you pronounce it arithmetic. That's what I've always heard anyway. So arithmetic sequences are formed by blank, a constant value to each successive term. The answer for that blank is adding. So arithmetic starts with an A, adding starts with an A. That helps me remember which one is which one's arithmetic, which one's geometric. That constant value that is added each time is called the common difference. Okay? Arithmetic sequences are going to behave just like linear functions, except for they are not continuous because we can only plug in whole numbers. So we have a bunch of dots that are in a line, but we don't draw the line through them for that. And arithmetic sequences have a constant rate of change. So they're going to behave like lines, but they're going to be dots instead of lines. So if we were to look at the arithmetic sequence given here, okay, this one is, whenever you see an N right here instead of an A with the subscript N, this is defined explicitly. Okay, so whenever you have the N, all you have to do is plug the N in. It's defined explicitly. This is just like, it's very much like having f of x equals 1/2 x minus 3. The difference is whenever it's a sequence, we can only plug in whole numbers for that. So if I plug in 0 right here, I'm just going to get -3. If I plug in 1, I'm going to get 1/2 times 1 minus 3. If I want to subtract here, I need common denominators. I'm going to get 1/2 minus 6/2. I will get 5/2 right here, and it will be negative. Or if you want to do -2.5, that's equivalent.
So how do you have negative numbers up?
Your answers can be negative. The input values cannot be negative. So what you get out can be negative, but what you plug in cannot be negative.
Okay.
So basically, like when you think of graphing this, it's always going to be like first and fourth quadrant. Your x coordinates are always positive in this case. Your y coordinates can be positive or negative. Here, for a 2, half of 2 is 1. 1 minus 3 is -2. For 3, you're going to have half of 3, which is going to give you 3/2 minus 3. Again, got to have common denominators there. 3/2 minus 6/2 will give you -3/2. We can plug in 4. Half of 4 is 2. 2 minus 3 is -1. And the last one will be -1/2 whenever we go through and plug that in. So if I look at this and graph those points, on the what is normally our x-axis, our horizontal axis, I would label that N. And my vertical axis, what's normally my y-axis, is going to be A sub n. And so I would graph the points. 0, -3 is right here. 1, -5/2 right here. 2, -2. 3, -3/2. 4, -1. 5, -1/2. Okay. We do not draw a line through it because it's not a it is not a function, it is a sequence here. Okay. Now a couple things to note about this. What is the slope of that line? It is up 1/2, which is 1/2, which is this number right here, right? 1/2 is also what we would call our common difference right here. So if you think of going from one term to the next, you are adding 1/2 each time. So the slope of that line and the common difference of that line are going to be related to each other. So if it's defined explicitly, if it just has an N like this, the number next to the end, that is going to be your slope. So it works just like it does with a line. The only difference is it's dots instead of connected. You could, yeah, you could if it was a calculator active situation, or you could like make you a table and just have like put your equation over here, and then Desmo, you could just type in 0, 1, 2, 3, 4, 5, and it would graph those points for you.
So the questions could ask you for the common difference, and then if they just give you it and define explicitly, it's already there.
Right. Right. They might. You never know on this. It's kind of like some of those like increase and decreasing questions. Some of them will be that straightforward. Some of them will not, which makes even the easy ones hard because you got to decide when it is the easy one and when it's not. Also another thing to note right here. Let me get a different color. Here was my -3. Notice that was this first point right here on my graph. My a sub 0, this point right here is my a sub 0 equals -3. Okay, those are some relationships that are going to hold true for all arithmetic sequences. That y-intercept of that graph, because if we think of it like a function, -3 is the y-intercept. That is your a sub 0 or your starting term for that. Okay, questions? All right, let's keep going. All right, so something that they might do is they might ask you what the common difference is. Sometimes this is very easy to find. Sometimes it is not. So common difference is the first thing that you want to look for here. So in example 10, we've got -5, -3.1, -0.07, 1.7. We've got to decide what's happening each time. So the first thing you would need to decide is it arithmetic or geometric or neither. Right now we're working on arithmetic, so you can kind of guess we're probably adding something. Although you can also subtract, because what's a way we could subtract and it really still be adding? You add a negative is the same as subtracting, right? So we say that arithmetic functions are always adding, but subtracting 4 is the same as adding -4. So that common difference can be negative for these. In this case, it's not because you are increasing, right? This one's not like super duper easy to find, just like looking at it. But what you can do every single time, always will work, is take a term, so like -3.1, and subtract the term before it. Right? So if I do -3.1 minus -5.5, that really is like we're adding there. And let's see, 5.5 minus 3.1 will give me 1.4, 2.4. 2.4, right? I think. Yeah, 2.4. So that common difference is 2.4. You can check it with the other terms, because if you take -0.7 and you subtract -3.1, because it doesn't matter which term you use. If you take a term and subtract the one before it, then you should get that common difference again, and this also gives you 2.4. So that common difference is 2.4.
What about the 0.7 to 1.7?
And I could have messed up. Is that still right? Let's see. If we do 1.7 minus, no, it's right, -0.7. It becomes like you're adding, and that'll be, it'll be 2.4 again. Yeah. Yeah, so it'll be 2.4. So that is your common difference. Okay, now, the common difference is going to be sort of the slope of the line, right? So if we were trying to do a problem like example 11, where we've got 6, 8, 10, 12, 14, what's the common difference for that problem? is 2. That one's a lot easier to see right off. But you could always still do the same thing. 8 minus 6 gives you 2. Or you could do 14 minus 12. You get 2. If you take any term, subtract the one before it, you get 2. So the common difference is 2. And then what is our starting value here? 6. So if I want to do A sub n, okay, then I can take I could write it a couple ways. I could write it with my common difference times n plus my starting value, which is like this, or the form I have it in down here looks more like this. A sub n equals 6 plus 2n. I think that box, no, maybe, hold on. Am I supposed to move that box? Why do I have that box right there? Let me go back over here and see what I had that box there for. I do not know why the box was there. I think the box was just originally behind that. Let me move it. I think that was just what it's supposed to look like. There. So, for an arithmetic sequence, you can always just write it like the equation of a line, where your A sub 0 is your starting value, and that common difference is your slope for that, if it wants an explicit formula for it.
But that's not how the sequence goes. It's just like putting it into a formula.
It is a formula that will give you any one of those values of your sequence. So like if you want to know like A sub 20, right? Then the formula that we had here was 6 plus 2 times n for that. So we could replace that n with a 20, and then we get 6 plus 40 and get 46. So this is an explicit formula, which will give you any term that you want. And you don't have to go in order. Like we don't have to do A sub 1, A sub 2, A sub 3 whenever it's defined like this. Okay. All right. So 12 asks us, what is the third term of an arithmetic sequence, or the third term of an arithmetic sequence is 9. And the fourth term is 13. What is the value of the 10th term? Okay. So they tell us that we have an arithmetic sequence. And I know the third term is 9. So that tells me A sub 3 is 9. And they tell me the fourth term is 13. Now, we are lucky here because they gave us terms that are right next to each other. So we can find the common difference. What's the common difference here? It's just 4, right? Because you would add 4 to get from one term to the next. So if we want to write an explicit formula for this, we could write it as A sub n equals. Now, here's the problem. I know I'm going to have 4 times n. But I need this to be my A sub 0 term right here. And I don't know what that is just yet, right? But I could start, let me write this down here. I'm going to put 13 here. I'm going to put 3. A sub 3 is 9 right here. I could just go backwards, right? A sub 2, A sub 1, A sub 0. So we could just subtract 4. So this is going to give us 5. This will give us 1. This will give us negative 3, right? And then we can take this and plug it in over here. So I could do A sub n equals 4n minus 3. And then it's asking me for the 10th term. So I could do a sub 10 equals 4 times 10 minus 3, which is going to give me 40 minus 3, which is 37. Now, that is certainly not the only way to get there, okay? And they like, this right here says it's a shortcut. Depending on how big the numbers get, it might be a shortcut. If the numbers are pretty small, like you've got here, you could always just do what I've just done. But there's some other ways we could have came up with a sub 10. Any ideas? What do you think?
You do negative 4 times 3 because it's the third term to get back to 0. So you do 9 minus 12, that's negative 3.
Okay. Yeah, so you could kind of see like we need 3 more terms in that direction. So we are going to multiply there. That will work. If we want our equation, did we have to find this equation right here? I knew my common difference was 4. Could I do this? Could I do a sub 5 and just add 4 and get 17? And then I could do a sub 6 and get 21. A sub 7 would equal 25. A sub 8 would equal 29. A sub 9 would equal 33. And a sub 10 would equal 37. Could do it that way too, right? That would work. If I was kind of thinking this way, sort of what you were just saying, Connor, how could I do this so that it would be even shorter so I didn't have to write every one of those down? How many times did I have to add 4? Now let's, starting from right here, right? I had to add 4, technically right here I'm adding 4, adding 4, adding 4, adding 4. So 1, 2, 3, 4, 5, 6 times. Okay, where could I have gotten that number 6 from? I could do 10 minus 4, right? Because I had to jump ahead 6 times, right? I was at 4. I needed to get to 10. So I could have said, well, I'm adding 4. I'm going to have to do it 6 times. 4, I could have done 4 times 6, and I could add it to the 13 that I had, and that'd be 24 plus 13, which would also be 37, right? So there's lots of different ways that you can do these problems. Now, one of the things that they have in our explanation for this section is that sometimes they'll give their answers in this form right here. So it's got a sub n equals a sub k plus d times n minus k. Okay? So n right here is what you're trying to find. In our case, it's 10. Right? Now, because we want to find a sub 10. But we don't have a sub 10. We got to start from somewhere, but it's not a sub 0 because they didn't give us a sub 0. I'm having to start either from a sub 3 or a sub 4. It doesn't matter which one you use, but I'll use a sub 4 right there, which a sub 4 is 13. And then I know my common difference for this one is 4. And then what I'm trying to find right here is 10. And where I was starting from was 4. So notice what that is there is 13 plus 4 times 6, which is what I just did, right? I said I need 6 more times here. So that is 13 plus 24, which is 37.
Where's the negative 4 come from inside there?
It's automatically negative because there's a minus sign.
Oh, negative.
The 4 is because we knew the a sub 4 term. That's the term we were starting from. Why did I not subtract what? Right here, you're going to get 10 minus 4, which is going to give you a positive 6. So that'll be a positive 24 there. Okay. Let's just look briefly at what a geometric sequence is. We probably won't get to do the problems here, but let's get this part filled in. So a geometric sequence is formed by multiplying a constant value by each successive term. That constant value is called the common ratio. Okay, and geometric sequences are going to behave like exponential functions. Except for they are not continuous. They will also just be a string of dots as well. And geometric sequences are going to have either an increasing or decreasing rate of change. It will not be a constant rate of change. And if you think about what you know about exponentials, they either start off slow at first and grow really fast, or it could be exponential decay, where something starts off dropping really fast at first and then more slowly. So you're going to see either increasing or decreasing rate of change for these. Let's look at the graph real quick for these. I'm going to do this pretty fast right here for these. So if I plug in 0, I would have 80 times 1/2 to the 0 power. Anything to the 0 power is just 1. So that is just going to be 80 right there. And then I'd get 80 times 1/2 to the first power. That's just half of 80. That's going to give me 40, sorry. Then I have to do 80 times 1/2 to the second power. Now when I square a fraction, I just square the top, square the bottom, so that'd be 1/4. So I'm doing 1/4 of 80, which is 20. Now, you should see a pattern in our y values. Such a good pattern that we could probably keep on going with this without actually having to plug the numbers in. What do you think the next one's going to be? It's going to be 10, and then 5, and then 2.5. Because our common ratio there is 1/2. We're just multiplying by 1/2. So that looks like this: 80, 40, 20, 10, 5, 2.5. There. We don't connect it because this is a sequence, so it's only points for that. And that's going to be as far as we're able to get today.